All right, so welcome to my presentation on efficient lattice-based polynomial evaluation and batch zero-knowledge arguments. This is a common work with Amin, Sakzad, Ron Steinfeld, and Joseph Leo. My name is Veronika Kuchta, and we are from Monash University in Australia. Okay, a brief overview of this talk is as follows. First, I will briefly review the preliminaries of this paper. Then I will introduce our first contribution on lattice-based polynomial zero-knowledge arguments. After that, I will discuss its security and efficiency analysis. Then I will move to our second contribution on lattice-based batch zero-knowledge arguments and discuss its security and efficiency analysis. Lastly, I will briefly mention the applications to the range proof. So let's move to the preliminaries. We are talking about lattice-based zero-knowledge arguments, so it's good to recall the definition of a lattice. And an n-dimensional lattice is the set of all integers, of all integer linear combinations of some basis set B, where this basis set B consists of n linearly independent vectors. Then our constructions are constructed over a polynomial ring R, which is defined as follows, as the set of all polynomials reduced modulo x to the n plus 1, where n is a power of 2, and the corresponding modulo Q ring, RQ, is defined as the set of all polynomials reduced modulo x to the n plus 1, where the coefficients are all reduced modulo Q. The security of our constructions relies on the hardness of modulo Cs and modulo LWE assumptions. Therefore, I will briefly recall them as well. So let R be a polynomial ring and K some distribution over this ring. Then given a random matrix A of dimension n times m, sampled from the distribution K, the problem is to find a non-zero vector V of dimension m such that the matrix vector product is equal to 0 modulo Q. And the Euclidean length of this vector is smaller than beta. Then modulo LWE assumption is defined as follows. Let he be a distribution over the polynomial ring RQ as being a secret vector sampled from the distribution of dimension n. Then LWE distribution is obtained by sampling an n-dimensional vector A and error E and outputting a tuple where the first component consists of A and the second component is the inner product of A and S plus E. So the problem is to distinguish between m given samples, which are either from the LWE sample or from a uniform sample. Okay, we are using a lattice-based commitment scheme in our constructions. Therefore, I will also briefly review the commitment scheme. It consists of the following three algorithms: the key generation algorithm, which generates a commitment key A, capital A. So it consists, it's composed by the two matrices A1 and A2, and this commitment key is used to commit to messages X, which are elements from the polynomial ring of dimension nu prime. And the commitment algorithm commits to a message X by choosing a randomness vector R of dimension m and outputs the commitment C, which is computed as A times R plus the encoding of X, where encoding of X is computed as the extension of X by the zero vector of dimension nu. So this encoding is applied to make the dimensions match. Then the opening algorithm is a relaxed algorithm. So we are using a relaxed commitment scheme. And this algorithm is defined as follows. And valid opening of a commitment C is a commitment which consists of a message X and a randomness R and a value D, which is the difference of the challenges. Then the verifier checks that d times the commitment is equal to a times r plus the encoding of x, and that the randomness is upper bounded by a parameter gamma. Otherwise, it returns 0. So we are constructing a zero-knowledge argument. Therefore, it's important to recall Sigma protocol. And the Sigma protocol is interactive proof between prover and verifier, which is defined for a relation R and a statement that witness pair V and W. And for two relations R and their corresponding relaxed relation R prime, where R is a subset of R prime, the proof system is a Sigma protocol with completeness error alpha and the challenge space. If it satisfies the following three properties, completeness property means that a transcript between an honest prover and honest verifier is accepted with probability at least 1 minus alpha, where alpha is the error, completeness error. The second property is the special soundness, and namely we are looking at the k+1 special soundness. It means that there exists an efficient extractor algorithm which can compute the relaxed witness that satisfies that the tuple V and W prime is an element of the relaxed relation, assuming that the extractor has access to k+1 accepting transcripts. And the last property is the special honest verifier zero knowledge property, meaning that there exists an efficient simulator that outputs a transcript given the public input and the challenge in the challenge space, such that this transcript is indistinguishable from an accepting transcript, which is produced by the run of the real protocol. Then the challenge space we are using in our constructions consists of a set of monomials, and our challenge space is reduced only to 3 monomials: x to the 1, x to the -1, and x to the 0. And the reason for that was that this was the suitable set which made the soundness analysis in the security proof possible. Okay, let's move to the main contribution, lattice-based polynomial zero-knowledge argument. And before we introduce the protocol, we first need to define polynomial commitment, how a polynomial commitment over lattices can be constructed. So let's assume f being a polynomial over the ring RQ, where the coefficients of these polynomials are all integers, reduced modulo q. This is a polynomial of dimension n-1. Let's assume that n can be written as m prime times m prime minus 1. Then another representation of n can be written in this way, decomposed into two sums, where the first sum runs over I from 0 to m prime minus 1. The second sum runs over j from 0 to n prime minus 1. And the coefficients are now indexed by j and I, and are also integers reduced modulo q. Then these coefficients can now be written into a coefficient matrix as follows. So the coefficients aj, I can be written into this matrix, so such that we have an n prime times m prime matrix. Then each row of this matrix can be written into a vector aj. So for instance, the zeroth row can be written into a vector a0, first row can be written into a vector a1, and so on. In order to commit to each row, we pick a randomness raj, and we compute commitment as a times raj plus the encoding of this row aj. Then, in order to compute to a polynomial, we need first to compute a polynomial vector f hat, denoted by f hat, and this is multiplication of the matrix A by vector of powers of x. This will be multiplied by the matrix of by the matrix A from the left. So this vector cannot be sent to the verifier in a direct way, because this would easily leak all the coefficients of the coefficient matrix and of the original polynomial. So it is also important to note that the original polynomial can be reconstructed from this matrix by first multiplying the matrix from the left by the powers of x, and then multiplying the result from the right by the multiple powers of x. Okay, since we know that the original matrix cannot be used for secure polynomial commitment, so that means we need to now mask that coefficient matrix A. And this can be done as follows. So we pick masking values uji for the corresponding entries of the original matrix A, and then we encode them into the monomials in such a way. So for instance, u0I is encoded into u0I times x to the n prime minus 1, then u1I is encoded into u1I x to n prime minus 3. So that means u2I would be encoded into u2I times x to the n prime minus 5, and so on until we get encoding of un prime minus 1I is un prime minus 1I times x to the power of 1 minus n prime. Then the masking matrix is constructed as follows. The first column remains the same, unchanged, and all the remaining columns will be masked. So we subtract from each original entry of the original matrix A the corresponding masking values as we have generated here. And additionally, we also need to add an additional row to this matrix, and this row looks as follows. So it consists of the following polynomials, where the last entry is 0. So the reason for adding this additional row is that we should be able to reconstruct the original polynomial f of x. If we multiply now this masked matrix by power of x vector from the left, and then by a multiple power of x vector from the right. So when we do this multiplication, for instance, if we didn't have this additional row, then we would not be able to reconstruct the initial polynomial, because there would be still those masking values in this polynomial. But by adding this smartly choose an additional row, we will be able to eliminate those masking values during the reconstruction, such that we indeed are able to reconstruct the polynomial. So this procedure of hiding a polynomial, of hiding the coefficient matrix, was one of the main contributions and challenges of this paper. So in order to commit to the polynomial, we again first send each row of this masked matrix into a vector. So the zeros row will be sent into a vector A0 tilde. So tilde now indicates that the vector is masked, the matrix is masked. And then we compute a polynomial vector f tilde x, which is this masked matrix A multiplied by the vector by the power of x vector. And then we compute commitment to each row by picking a randomness to each row, Raj, and the commitment is computed as A times Raj plus the encoding of the masked vector, of the masked row. Okay, and the corresponding commitment to the last row is denoted by U. So then, in order to commit to this polynomial vector f tilde, we first need to compute the randomness in the following way. So we collect now all the randomnesses we used for the row commitments, and we multiply them by the corresponding power of x. Then the commitment of f tilde is computed using this new randomness, this computed randomness. And the secret is that polynomial vector. So this would be A times R tilde plus F tilde. And it can be proved that this is equivalent to the sum of the row commitments multiplied by the power of x plus the last row commitment multiplied by the by x to the power of n prime. Okay, now since we know how we can commit to a polynomial, we can construct a polynomial evaluation protocol in the following way. So we prove knowledge of an evaluation value of a polynomial f of degree n minus 1. So we note that f of x can be written as q of x times x minus v plus w, where v should be the evaluation value. So that means f of v should be equal to w, right? So this representation holds. And it is clear that q of x is a polynomial of degree n minus 2. So again, now we need to apply exactly the same procedure to q as we have done for f. So we decompose q into this representation, and then we compute the corresponding coefficient matrix. Then we mask this corresponding coefficient matrix. So the corresponding coefficient matrix of the original polynomial q was t. The corresponding hiding or masked coefficient matrix is t tilde, which is a bigger matrix by one row and one column. And the last row of this matrix, this additional row, is denoted by S. And then the commitment to each row is denoted by capital T tilde, is computed exactly in the same way as as we have showed for F. Okay, what we want to prove is are the following two relations. The first one is defined as follows: the secret inputs to the prover are v, w, the two polynomials f and q, and the randomnesses are v and rw. The inputs to the verifier are the commitments to v and w. And the relation that needs to be proved is that f of x can be written in this way, and the evaluation of f and v is equal to w, where the randomness, where the Euclidean norm of the randomnesses should be upper bounded by beta. Similarly, since during the security proof, when we are proving the soundness of our construction, we are able to construct a relaxed witness, not the original witness. So we need to define a corresponding relaxed relation, which is defined very similarly to the original relation. So by hat, we are now indicating that we are indicating the relaxed relation. Okay, now the protocol itself looks as follows. It consists of the following steps. The common input to the protocol are the commitments to V and W. So basically the common input is C, V and CW. Which are commitments to V and W using the corresponding randomnesses RV and RW. And so the first step in the protocol is performed by the prover, and the prover computes the following statement. So the prover runs the polynomial commitment algorithm protocol on input of polynomial f and the capital and the commitment key A, and the corresponding parameters and the sizes of the coefficient matrix n prime and m prime. And the same protocol is run for the polynomial q in order to compute the corresponding row commitments. And then the values v and w need to be masked by picking masking values mv and mw. Then we compute the corresponding commitments to those masking values using the randomnesses rmv, rmw. And so the public commitments are now the commitments from those two polynomials, and the commitments to the masking values, they are sent to the verifier. And the secret values, which are the corresponding randomnesses, they are kept by the prover. Then the verifier sends a challenge to the verifier, which is an element from the challenge space. As I mentioned before, we are using a challenge space consisting of 3 monomials: x to the 1, x to the minus 1, and x to the 0, so 1. So the prover's response consists of the following steps. After receiving the challenge, the prover computes f tilde of x. This should be small x, indicating the challenge. So small x is the challenge. And q tilde x, as it is done in the polynomial commitment. And then it computes the corresponding randomnesses. So the prover will need to commit to now to this polynomial vectors f tilde and q tilde. So he first computes the corresponding randomnesses by collecting the randomnesses of the corresponding row commitments. And so these are rf tilde and rq tilde. And then it computes the commitments to f tilde and q tilde. It also computes the commitments to 0 using the randomnesses rf and rq. Then it masks the values v and w by computing involving the received challenge. So it computes xmv being equal to mv plus x times v, and xmw is mw plus x times w. And it also computes the corresponding randomnesses, and then sends that all these computed values which have been computed in the steps to the verifier. Then the verifier checks the verification equations, and it also checks that the Euclidean norms of the randomnesses are small, so upper bounded by a particular upper bound. Now, after having introduced our main protocol, I will go only briefly through the security analysis. So the polynomial evaluation protocol achieves completeness, special honest verifier zero knowledge, and 3 special soundness for extracting a breach on the binding property of the used commitment scheme, or extracting openings to the polynomials. So the binding property relies on the underlying MCs assumption, while the zero knowledge property is guaranteed by the hiding property of our commitment scheme. So here I just want to briefly show the idea in order to prove the special soundness of our protocol. This can be proved by reduction to the binding property of our homomorphic lattice commitment. And as I mentioned, the challenge space consists of 3 challenges. Then these values can be used to generate a generalized van der Monde matrix, which has this form. And this van der Monde matrix can be used during the extraction procedure. So the extractor can compute CF, which can be represented in this way. Then the extractor can evaluate the CF tilde in each of those challenges, x kappa, where kappa is running from 1 to 3. So there are 3 challenges. And then the extractor computes, so we denote the evaluations of those commitments in the corresponding challenge by a small c kappa. Then we compute a c kappa minus the 0 commitments, and we obtain the encoding of the powers of the masked values of A and masked values. So here's a tilde missing. Then we can write CK into a matrix C by for each of the challenges. Then we define a van der Monde matrix V3 as follows. So this is a van der Monde matrix of which consists of 2n prime minus 1 columns. And this is the size of Vandermonde matrix which we need in order to extract the corresponding witness. And so this can be decomposed into the following concatenation of the 3 times 3 Vandermonde matrices. And then we can say that this matrix C, which resulted from this step, is equivalent to the Vandermonde matrix, to this Vandermonde matrix multiplied by the extracted witness, by the relaxed extracted witness. And in exactly the same way, we can extract also the randomness. So then the special honest verified zero knowledge property can be proved by showing how we can simulate an evaluation of the polynomial f of x at a certain point, challenge point x, and then we reduce the security to the hiding property of the used lattice commitment scheme. Okay, this is the efficiency analysis. Here we can see the proof sizes have been generated for different sets of parameters, and sets of parameters differ between the different sizes of the ring dimension n and the modulus q. The security analysis has been evaluated for a security parameter of lambda being 128. Okay, and now we are running out of time, so I will briefly introduce our second contribution, which basically applies our first contribution as its main part. So the second contribution is batch polynomial evaluation protocol and zero knowledge evaluation protocol. Here, the prover knows a vector A and the two polynomials P and Q, such that P of A, so P, polynomial P related in the vector A should be equal to 0, and Q is an opening to a commitment of Q of A with some randomness R. So we assume vector B being a publicly known vector. Furthermore, we assume that the polynomial P of A is defined, is a polynomial vector of length LP, and polynomial vector Q of A is a polynomial vector of length LQ. So each of those components, PIA, is a LA variate polynomial, and QJ, so each of those components, QJ, is an LA plus LB variate polynomial. P and Q are vectors of polynomials of total degree dp and dq. So for our construction, we assume that dp is equal to n, and n again is equal to n prime minus 1. Okay, so we know that aj1 is a vector of LA monomials. So that means it can be written as this in this form. So we built a coefficient matrix of these monomials in the following form. Then again, we mask this matrix to A tilde using exactly the same technique as introduced in the first contribution. Then each row of this matrix is denoted by AJ tilde, AJI tilde. So the matrix BJI is public and doesn't need to be masked. And that's all as the preparation for the protocol, what needed to be mentioned. And what we want to prove in this protocol is are the following two relations. So for all, here are indices missing, J and I running from I is running, J is running from 0 to m prime minus 1, I is running from 0 to m prime minus 1. So we are defining the following two relations. Prover's input is the secret vector A tilde and the corresponding randomness vector, and verifier's input are the commitments Cj, which are the commitments to the vector Q evaluated at A Ji tilde and Bji, and the polynomials PQ. So the condition, the relation which needs to be proved is the evaluation of P in this value in this vector, in this masked vector AJI should be 0, and the commitments CJ are the corresponding commitments of Q evaluated in AJI tilde and BJI with the corresponding randomness RJ. And in the same way, the relaxed relation is defined. Then the batch polynomial evaluation protocol consists of the following parts. The common input to the protocol consists of the vectors CJ, which are computed as commitments, as I mentioned already before. Then common reference string is generated by generating Lagrange polynomials, Lj and Yi, where Yi being the distinct challenge values. And so L0 of x is computed as the product of x minus yj, and Lj of x is computed as follows. So these are the Lagrange polynomials. Then public input to the protocol are PQ and vectors BJI and commitment CJ. Provers witness are the secret masked vectors AJI and the corresponding randomnesses of CJ. And CJ shouldn't be here. So the first statement of the first step of the protocol is performed by the prover. So the prover basically sets AJ being the equal, being a vector from AJ0 to AJM prime minus 1. And the prover needs to show that the vector AJI tilde, the masked vector, and BJI satisfy the above polynomial relations defined in the two relations. And this is done, basically, I'm now trying to speed up, by performing some computations summarized here, and it computes a protocol. In this first step, the prover needs to compute a protocol Pij star of x, which has the following form. And to prove that Cj's are commitments to a Q on input AJI and BJI, the prover will pick random vectors C1 to Cm prime and compute another polynomial Qij of x, which can be represented as follows. Then on input of these two polynomials, Pij star and Qij star, and an evaluation value u and the corresponding function value is evaluated at this value u, the prover will run the prover part of the polynomial evaluation protocol from the first contribution. So the output is denoted by a message and statement. So the message is the consists of the commitments in this protocol, and statement is the state consists of all the randomnesses which were used in this protocol. Okay, and then the challenge, the next step is the challenge sent by the verifier from the challenge space. And after receiving the challenge, the prover needs to respond to the challenge. Again, now running the polynomial evaluation protocol on the state, including the challenge, and the output will be denoted by message 2. So here denotes that this is done for each of the two polynomials, Pi star and Qi star. Then additionally, the prover needs to compute some additional values and sends all those values, the message AI hat, R hat, and S hat to the verifier. Then the verifier runs the verification part of the polynomial evaluation algorithm protocol on all those values, and checks also the smallness of the responses. The security of analysis and security and efficiency, I only briefly mentioned the security definition. So the batch protocol also achieves perfect completeness, special, honest, verify zero knowledge, and special soundness, assuming that the underlying polynomial evaluation zero knowledge argument is secure. So the security is of this protocol of this batch zero knowledge argument is reduced to the security of the underlying polynomial evaluation zero knowledge argument. And the evaluation of our protocol can be observed here. So this again has been computed for different parameter sets, and we can see the corresponding proof sizes. And the last part was to apply our protocol, our main contribution, the polynomial evaluation protocol, and then its extension, the batch polynomial evaluation protocol into the range proof. So the idea is that using the batch polynomial evaluation protocol, we can construct the corresponding range proof. And since I'm already out of time, I only want now present the results of our range proof, of the range proof which we constructed using our batch polynomial evaluation protocol. And this has been compared with the crypto paper from 2019, and the reference you can find in the paper. And as you can see, the main conclusion is that yeah, our approach, we can see, for instance, for smaller parameter sets, the difference from the crypto paper is not that big, but the difference becomes bigger the larger the number of batches we are considering in our protocol. So what we can conclude is that our approach achieves a significant improvement in the number of batched instances from a number of 1,155 batched instances, we can realize an improvement in the proof size compared to that range proof presented in Crypto 2019. So we also showed that for a higher number of batched instances, we achieve a more significant difference to this crypto paper. And namely, our proof size grows approximately by a square root factor of the batched instances, while the proof size in the crypto paper grows almost linearly. And this can be also observed here in this graph. Okay, that's all. Thank you very much.